Hello out there, and welcome to my channel. This channel is for educational purposes, and we like to take really deep dives into things that I believe are great theories of everything, or all-encompassing theories that you can hang your hat on, and that you can build your alternative paradigm or your holistic worldview upon them. And today is our 415th video that we've done on the reciprocal system of theory. And this is a system of theory that was arrived at by one Dewey B. Larson back in the 20th century. In about 1959, he proposed his two fundamental postulates about how the universe operates. Then, through a process of deduction, he deduced a theoretical universe. Basically, through a process of if this, then that. He constructed a theoretical universe about what the universe would look like if his two postulates were correct. And then he wrote a number of books over the remaining 30 years of his life. And he on physics and chemistry and astronomy, also on economics, and a book on metaphysics, which includes stuff on philosophy and religion and psychology and biology. And I'm sure if he would have lived long enough, he would have branched out into other theories as well, and some of his followers have. But in his books, he basically compares his theoretical universe with the empirical universe of the legacy scientists, what they have measured in their laboratories and compiled in their tables. And we are looking at one of his books today called Basic Properties of Matter. And this is on chemistry. And so he takes his theoretical universe and derives equations for the basic properties of matter, such as today we're going to be starting a chapter on inter-atomic distances. He's also got sections on temperature relations, like the boiling point and the melting point, the critical point, the compressibility, and we will be going through those. I don't know that we're going to go through this whole book because we're moving very slowly, but we would definitely get into the meat of it anyway. Now, the Larson's two fundamental postulates are dominated by the first postulate. And the first postulate says that the universe is composed entirely of one component: motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So, more or less, the universe is not made out of matter, not made out of energy. It's made out of motion. Specifically, it's made out of a kind of motion he calls scalar motion, which is a directionless motion. It does not have a specific direction, but it does have a magnitude. And you can visualize this using a balloon with dots on it. If you blow up the balloon, all of the dots are moving away from each other. And in fact, even the points between the dots, the locations between the dots, are moving away from each other also. Every location is moving away from every other location. But they're not moving in any specific direction. They're just all moving away from each other. If you suck in the balloon, they will all be moving toward each other. And it will actually look like they're gravitating. If you take one dot and call it the reference point and assume that it is motionless, all of the other dots will be moving toward that one dot. And it will look like there is a gravitational field around, and mathematically, it will look that way as well. So Larson calls that an as-if force. The outward motion Larson calls the progression, and the inward force Larson calls gravitation. And motion is the relationship between space and time. That sets up a generalized reciprocal relationship between space and time. Space and time are basically identical, but they are reciprocals of one another. Just like 3/1 and 1/3 are reciprocals of one another. They have the same qualities, but they have them in a different order. And space and time, motion is basically a fraction with space or time as the numerator and time or space as the denominator. And motion comes in many, many different varieties. All of our basic scientific quantities are forms of motion, such as matter and energy, speed, acceleration, force, pressure, viscosity, fluidity, electric charge, electric current, magnetic flux, electrical capacitance. These are all power. These are all forms of motion, and they all have their individual signatures in terms of space and time, such as speed is space over time, energy is time over space, pressure is time over space to the 4th power, matter is time to the 3rd power over space to the 3rd power, acceleration is space over time to the 2nd power. These are all different kinds of motion, and they're represented by fractions of space and time. But space and time can have 3 dimensions. That's what Larson calls coordinate space and coordinate time. These are really our reference systems, spatial reference systems. This is a 3 dimensions of space in a still frame. That is our spatial reference system. But and that we notice, in our environment, we can see X, Y, Z coordinates in space or volume. But since space and time are reciprocals, Larson also extrapolates and arrives at a temporal or time reference system that is 3 dimensions of time in a still frame. And then also time and space have only in discrete units. You have to have a full unit of space in order to have space. You have to have a full unit of time in order to have time. And if you don't have a full unit, then you don't have that entity. And if you have 1 unit of space in 1 unit of time, space over time being speed, 1 unit of space and 1 unit of time is what Larson calls unit speed. 1/1 = 1. And this unit speed is also the speed of light. And this is the background motion of the universe. The speed of light outward in all directions is omnipresent. It's always existing. Okay, so that is what you have when you have a universe of motion. When you have a universe of motion, even in an empty universe that has nothing in it, you still have motion. Motion precedes the thing that's moving. So you have to be able to conceive of motion without anything moving. That is your empty universe. Larson calls that the progression of the natural reference system. Motion in outward in all directions at the speed of light. And that is the basic motion that the universe is constructed out of. And you basically construct the universe by superimposing other motions on that progression. Other motions also include rotation, vibration, and rotational vibration. Rotational vibration would be like that. Vibration is like that. Rotation, and then rotational vibration. And these different kinds of motion can be superimposed on this outward progression. And you end up creating first subatomic particles, and then atoms, and then molecules, and then aggregates of molecules, all the way up to the largest galaxies. Now, if you have this background progression of the natural reference system as your neutral point or your null point, your 0 point, then that means that half of the universe is moving faster than the speed of light. Half of the universe is moving slower than the speed of light. Larson refers to these as the cosmic sector and the material sector, respectively. The material sector is really the only sector that the legacy scientists know about. Einstein said that the speed of light is the maximum speed of the universe. Larson says that the speed of light is the midpoint of the universe. So there's an entire half of the universe that Einstein and his followers are unaware of. It's called the cosmic sector, and that is where you have cosmic matter, which they call antimatter, or mesons. And those two sectors are reciprocals of one another, meaning that they have identical qualities, except they are in reverse reverse roles of space and time. So in the material sector, you have coordinate space, 3 dimensions of space in a still frame, or the spatial reference system, moving through clock time, the scalar motion in time. The clock is always getting... Well, I used to say the clock is always getting later and later and later. I'm not quite sure of that anymore, so I'm instead going to substitute the clock is always getting, time is always getting farther and farther and farther apart, like on the surface of an expanding balloon in space. So in the cosmic sector, then we have 3 dimensions of time in a still frame, a temporal reference system, moving through space, clock space, a scalar motion through space. Space is always getting farther and farther and farther apart. So they're the same, except they are in the roles of space and time are reversed. So too, within the material sector, you have what he calls the time region. And the time region is a region where the interactions of atoms and molecules, for example, are occurring in such a small space that there is no space because of the discrete unit postulate. You have to have a full unit of space before you have space. And so if particles are interacting in less than that amount of space, there is no space and there is only time. Because the universe is made out of space and time, motion, space and time. So if it's not space, then it has to be time. So this time region is the region of interaction of atoms and molecules. And when you cross the boundary into this time region, the rules invert again. And now, like in the normal outside region, you have the progression is moving particles away from each other and gravitation is moving particles toward each other. But in the time region, the progression is actually moving particles toward each other, and gravitation is moving particles away from each other. Gravitation moves particles toward unit distance, and the progression moves particles away from unit distance. And the same thing is happening in the cosmic sector, except with space and time interchange. So you have what Larson calls the space region, that is within 1 unit of time. And cosmic gravitation and cosmic progression move in the opposite directions once you cross those boundaries. All of this forms kind of a yin-yang arrangement that you can, you'll be able to see that if you look at my thumbnail that I've started putting up. That is kind of a map. It gives you the all the four sectors of the universe and the three boundaries that are involved. So now Larson takes this and he moves into discussion here, chapter 2, Inter-Atomic distances. Now we left off with the end of chapter 1, where Larson proposed his equation for the specific rotation and was connecting it to the meaning of the interatomic distance. Hopefully he will sum some of this up. I'll try to fill in the gaps. Again, I just have to mention that I do not understand this stuff. To the best of my ability, like I said yesterday, I think I'm getting about 60 to 70% of this after having gone through it several times. You know, maybe my acumen for science isn't really that good because I'm a liberal arts person, but I think actually I'm pretty well positioned to understand this stuff because I'm kind of a bulldog, but also because I don't have an extensive science background. And so I don't have all kinds of stuff to unlearn that is a characteristic of paradigm shifts. So, but I'm not a master of this, and I don't believe there is a person on earth who is, including even Larson when he was alive. Larson made a lot of mistakes. I believe his theory is correct. Whether he applied it correctly all the time, I don't agree. I don't think so. And I think that there are some people that have come along and have made some revisions to Larson that were on point as well. Dr. Bruce Perrett. Unfortunately, Dr. Perrett died in 2020. And Dr. K.V.K. Nehru. And Nehru, I believe, is still with us here. But you know, I don't agree 100% with his interpretation either. So that's kind of what we're doing, is we're trying to kind of construct a little bit of a consensus here, or just kind of get an understanding of where Larson's coming from. Okay, so let's start this interatomic distance chapter. As equation 110 indicates, the distance between any two atoms in a solid aggregate is a function of the specific rotations of the atoms. Okay, now again, an atom is a combination of rotations. First, you have two, either, well, depending on who you follow, Larson or Perrett and Nehru, you have two photons at the core of every atom. Now, for Larson, these are vibrational motions. They are simple harmonic motions for either one of them, wave-like motions. A particle wave or a particle, a photon. But the photon at the core of the atom is either a vibration for Larson or a double rotation, counter rotation, or birotation for Nehru and Perrett. But that photon then is rotated, it must be rotated in 3 dimensions. Again, remembering that the universe is 3-dimensional in Larson's postulates. And so it has to be rotated in 3 dimensions to get it to basically to gravitate. Okay, so every atom has a 3-number grouping, not like, so like the periodic table is just 1 number, but for Larson it's 3 numbers. The primary 2-dimensional rotation, secondary 2-dimensional rotation, and then the optional 1-dimensional rotation that's opposite. And the first 2 rotations alternate in general as a statistical principle. Okay, so 2 atoms in a solid aggregate is a function of the specific rotations of the atoms. Since each atom is capable of assuming any one of several different relative orientations of its rotational motion, it follows that there are a number of possible specific rotations for each combination of atoms. Just to complicate things further, this number of possible alternatives is still further increased by two additional factors that were discussed earlier. The atom has the option, as we noted in Chapter 10, Volume 1, the book called Nothing But Motion, of rotating with the normal magnetic displacement and a positive electric displacement. When Larson uses the word displacement, he basically means motion. He's talking about the difference between the progression of the natural reference system and this motion. So it's not a motion per se, it's a displacement of an already existing motion. Okay, so Chapter 10, Volume 1 of rotating with the normal magnetic displacement and a positive electric displacement, or with the next higher magnetic displacement and a negative electric increment. Okay, so for example, you can have the oxygen. Oxygen, you can think of it as neon -2. You know, oxygen is number 8 on the periodic table. You could think of it as a neon rotation. A neon is I believe 3-2, and then you could think of it as 3-2 -2. Or actually, I guess it would be 2-2 -2. Or if you're taking it from helium, element number 2, which is 2-1-0, you could also think of oxygen as 2-1-6. So there are two different orientations of oxygen. And statistically, normally it would be 2-2 -2. But there might be certain circumstances where it's 2-1-6. And if it's closer to the middle, such as carbon, carbon could be either 2-1-4 or 2-2 -4. And both of them are statistically about the same. So you would be able to see carbon in two different forms of carbon commonly. Now, that's, again, making this a little bit more complicated, but I just have to mention that even with all of the complication involved in all of this, it's still a million times simpler than the crap that they teach you in school. Okay, it seems like what you're learning in chemistry class is simpler because you learned it so long ago, and you were open to it, and you needed to learn it in order to get a passing grade or whatever. This system is way simpler than that, but there's a lot of baggage that you have to brush off before you get to that point. Okay, so and in either case, the effective quantity, the specific rotation, may be modified by extension of the motion in a second vibrating unit as brought out in Chapter 1. I'm still not completely clear, even though at one point I think I used to be clear about this, but I don't quite understand what he means when he's saying the extension of the motion to a second vibrating unit. He discussed this in Chapter 1 at the end, and it left me behind, I have to say. But I don't believe that it's completely necessary to understand that right now, and I also believe that it will be explained further as we go along in this book. So just put that in the back of your mind, and we'll get it resolved eventually. It is possible that each of these many variations of the magnitude of the specific rotation and the corresponding values of the interatomic distances may actually be realized under appropriate conditions. But in any particular set of circumstances, certain combinations of rotations are more probable than the others. And in ordinary practice, the number of different values of the distance between the same two atoms is relatively small, except in certain special cases. As matters now stand, therefore, we are able to calculate from theoretical premises a small set of possible interatomic distances for each element or compound. Ultimately, it will no doubt be advisable to evaluate the probability relations in detail so that the results of the calculations will be as specific as possible. But it has not been feasible to undertake this full treatment of the probability relationships in this present work. In an investigation of so large a field as the structure of the physical universe, there must not only be some selection of the subjects that are to be covered, but also some decisions as to the extent to which that coverage will be carried. A comprehensive treatment of the probability relations wherever they enter into physical situations could be quite helpful, but the amount of time and effort required to carry out such a project will undoubtedly be enormous, and its contribution to the major objectives of this present undertaking is not sufficient to justify allocating so much of the available resources to it. And again, when Larson is saying the available resources, he's basically just referring to himself, because he is the only person working on this. And so you have to cut him some slack, when you're comparing what he's doing with the army of legacy scientists that are out there with billion-dollar grants and so on, coming up with their various, mainstream theories about this stuff. Larson is just one guy with, this enormous task. And maybe he got a little help from some other people once in a while, but it was pretty much, he had one lifetime to get this done. And so he had to make difficult choices about what to focus on. Similar decisions as to how far to carry the investigation in certain areas have had to be made from time to time throughout the course of the work in order to limit it to a finite size. It might be well to point out in this connection that it will never be possible to calculate a unique interatomic distance for every element or combination of elements, even when the probability relations have been definitely established. As in many cases, the choice from among the alternatives is not only a matter of relative probability, but also of the history of the particular specimen. Where two or more alternative forms are stable within the range of physical conditions under which the empirical examination is being made, the treatment to which the specimen has previously been subjected plays an important part in the determination of the structure. Okay, so I believe that has to do with more cosmic conditions, the ionization level, and things like that are really more in the purview of astronomy. It does not follow, however, that we are totally precluded from arriving at definite values for the interatomic distances. Even though no quantitative evaluation of the relative probabilities of the various alternatives is yet available, the nature of the major factors involved in their determination can be deduced theoretically, and this qualitative information is sufficient in most cases to exclude all but a very few of the total number of possible variations of the specific rotations. Furthermore, there are some series relations by means of which the range of variability can be still further narrowed. These series patterns will be more evident when we examine the distances in compounds in the next chapter, and they will be given more detailed consideration at that point. The first thing that needs to be emphasized as we begin our analysis of the factors that determine the interatomic distance is that we are not dealing with the sizes of atoms. What we are undertaking is to evaluate the distance between the equilibrium positions that atoms occupy under specified conditions. In chapter 1, we examine the general nature of the atomic equilibrium. And again, that equilibrium is established at the place where the progression of the natural reference system, which is pulling all atoms toward each other in the time region, and the force of gravitation, which is pulling all atoms away from each other in the time region. Where those two forces, or as-if forces, are equal, that is where you have the equilibrium. The forces are equal, and so you have to, and the progression is constant, and gravitation is variable. So you have to find the spot where gravitation is equal to that constant value of the progression. Okay. In this and the following chapter, we will see how the various factors involved in the relations between the rotations of the apparently interacting atoms, the as-if force, the apparently interacting atoms, affect the point of equilibrium. And we will arrive at values of the interatomic distances under static conditions. Then in chapter 5 and 6, we will develop the quantitative relations that will enable us to determine just what changes take place in these equilibrium distances when external forces in the form of pressure and temperature are applied. Okay, so first we're going to determine the interatomic distances under static conditions. He will do that in this chapter. In the next chapter will be on compounds. This chapter is just on atoms. And then in the later chapters 5 and 6, we're going to explore, well, what happens to these interatomic distances under the forces of pressure and temperature. You know, when you compress them, that's moving them closer together. When you heat them, that's going to expand them. So those two forces are also relevant to the interatomic distance. But first, you got to figure out what the interatomic distance is, like under kind of an abstract standard temperature and pressure. And then you add in that stuff later. Okay, we're going to stop there. And we will probably read the same paragraph, this last paragraph, over again tomorrow, but we will move into the meat of this chapter then tomorrow. Don't get discouraged. This will all add up, I believe. You stay with it. Thanks for tuning in.